So using these Maclaurin series for e to the x, sine x, and cosine x that we just found, or any other power series that we can easily find, we can find newer power series, for more complicated functions by using these techniques. We can substitute into a series, multiply or divide a series by a constant or a variable, add or subtract two series, or we can differentiate and integrate a series. So for example, if we want to find a Maclaurin series for x cosine x, well, we already know the Maclaurin series for cosine x, which is here, so we can just multiply it by a variable, which is x. So when we multiply this general term by x, we just add 1 to this exponent to get x to the 2n plus 1. Or you can think about it as distributing this x to each of these terms individually. Here we want to find this limit. Of course, we can use the L'Hopital's rule to find this limit. Using the L'Hopital's, we just get the limit as x approaches 0 of e to the x over 2, which is equal to 1/2. Or we can use power series to do it. So first, we do e to the x minus 1, and replace e to the x with its Maclaurin series, which is this. So when you subtract 1 from this Maclaurin series, you just delete this initial 1 term, and you have the rest of the series left over. And then if we divide each of these terms by 2x, we get this. X divided by 2x is 1/2, and then all the other terms still have an x remaining after the division. So when all these x's are equal to 0, they'll all cancel out, and we just have 1/2 remaining, which of course agrees with the answer we got using the L'Hopital's rule. We can also use power series to approximate a definite integral. So it's pretty hard to integrate this just using normal techniques. So we can approximate it with a power series. So before we can integrate it, of course we need to find the power series for e to the negative x squared. And since we know the Maclaurin series for e to the x, we can just substitute negative x squared for x in the power series for e to the x. So the Maclaurin series for e to the x is just x to the n over n factorial. So we replace the x with negative x squared. And then distributing the exponent, we get negative 1 to the n power times x to the 2n. So this is an alternating series because of this negative 1 to the n power. So next, we can integrate this. So integrating, we raise the power by 1 and then divide by the new power. And we have this from 0 to 1. And the expansion looks like this. So we have this evaluated at 1 minus this evaluated at 0. But this evaluated at 0 is just 0 because every term includes an x. So they're all going to be equal to 0 if we plug in x equals 0. So to get the value of this definite integral, all we really have to do is find the value of this when x equals 1, which is over here. So we need to find the value of this infinite series. And of course, it's kind of hard to add up an infinite number of terms. So we want to, we can just use a partial sum, but first we need to figure out how many terms we should add up in order to get an answer that is accurate to the 0.001. We want our error in approximation to be less than this. So to figure out how many terms we should add up, we can use the alternating series remainder theorem, which remember says if we add up the first n terms in an alternating series to approximate the sum, then the error will be less than the n plus 1 term. So first we solve for which n, the first term that will be less than 0.001. And just playing with the numbers, we can find that when n equals 5, the term is less than 0.001. So then we should use 5 minus 1, or when n equals 4, we should approximate the sum by adding up the terms until n equals 4. And then our error will be less than 0.001. So now we can add up until n equals 4 using a calculator, or you could do it by hand if you really wanted to. And so we get 0.748. And you can check on your calculator, evaluate this integral, and you'll probably get an answer that's really close. So now we're going to look at more, with error and approximation using these Taylor series. So if we use a Taylor polynomial up to n to approximate the value of a function at a point x, then we can define the remainder as the error in approximation. So the error is going to be the value of the real value of a function minus the approximated value using a Taylor polynomial. So it turns out we can find an upper bound for this remainder, and this is called the Lagrange Error Bound. So the absolute value of a remainder, when we approximate a function using n terms of a Taylor polynomial and approximating the value of the function at x, then the error is less than or equal to m, which is an upper bound for the n plus 1 derivative of f of x between c, the center of a Taylor polynomial, and x, the value where we're approximating. So m over n plus 1 factorial times the absolute value of x minus c to the n plus 1 power. And it's a little easier to understand when you look at an example. So let's say we want to find an upper bound for a remainder, which is just this Lagrange error bound, this Maclaurin polynomial of e to the x to approximate e to the x at x equals 0.1. So this series goes up until n equals 2, because the highest term is x squared. And it's a Maclaurin polynomial, so it's centered at 0. So we need to find m. So n is 2, so the n plus 1 derivative of f of x is the third derivative of e to the x, which is of course e to the x. So on this interval between a center c, which is 0, and the point where we're approximating 0.1, the maximum value of the n plus 1, or third derivative, of a function e to the x is going to be e to the negative 1. That's the maximum value that the third derivative can have on this interval. So we can say m is e to the 0.1. And then we plug that in for m, and then n is 2, so 2 plus 1 factorial, and then x, the point where we're approximating at, is 0.1, and c, the center of a Taylor series, is 0. So 0.1 minus 0 to the third power, n plus 1. So then, calculating this out, we get that the maximum error in approximation is this number. So approximation is pretty accurate.